Hello, my name is Antonio and I'm gonna explain my project on predicting the volume of emergency calls with Spark. Let me start with the problem and why it is important. Well, in the US alone, there are an estimated 240 million 911 calls being made each year. By being able to model the frequency of these calls, we can have a better logistics for fire departments, which means we have less resources being wasted and a quicker response time, which also translates to more lives being saved. Since many cities make their 911 call logs available online, it is much easier for us to obtain this data. For our experiments, we use the Seattle Open Data Portal. So Seattle is a large city, right? So it means we have a large volume of calls to train our model on. From their portal, we use two datasets. First one being the 911 call log, and the second one is the neighborhood map, which has information about fire stations, including address, name, and geographic coordinates. However, not all the information is available on these datasets. Most importantly, we don't know who responded to a call. This means that we require some pre-processing to do this matching before we go into training. And this is a really important step in our application, and I'm going to go into details later on how I do the pre-processing. A little bit about the model now. I use a regression model to predict the amount of incidents for different types of events. To build this model, I rely on the water framework, which is an open source alternative to TensorFlow and Caffe. I decided to use water because it can easily be integrated with Spark through the sparkling water package for Scala. And this integration is really easy. Before we train this model, we gotta go through the pre-processing, as I said. So basically, we lack the relationship between our data sets, and we wanna find out which fire station responded to a call. So we gotta make a few assumptions about this. So I assume that the closest fire station responded to a call, and the closest following the Haversine distance, right? The Haversine is a distance commonly used for navigation. Ideally, you would like to use Google Maps based distance, but for the sake of simplicity, I rely on the Haversine for this project. And I have two implementations of this distance. First one is the CPU, and the second one is the GPU. So I have a CUDA implementation, which I implemented myself, that is imported through the GPU enabler package from IBM. Unfortunately, this package has no data frame support. As I use data frame heavily in my implementation, I have to go from and to data frames, which incurs into some overhead, but it's not that bad. So, okay, this is basically the pre-processing. So the whole application I can break into four steps. I start by loading the Seattle Open City data. Then I'm going to a first pre-processing stage where I'm going to merge the call log and the fire station information into a single data frame. This means that I'm going to compute the distance between fire stations and incidents and decide which one is the closest, right? Then I go to a second pre-processing stage where I'm going to group my data based on selected features, such as month of the incident or type of the incident. And then I'm going to use this to count the different types of occurrences, right? So, and then I pass this data to my deep learning model, and I perform the training. So let me go to my source code real quick. So here, basically, I won't have time to cover all of this. That's not my goal. I just want to cover some main important topics. Before going through any processing step, I'm going to set the some execution parameters. The most important being force all jobs. When you set this to false, it will try to cache some of the pre-processing steps. It uses Hadoop for that. So if you want to train your model again, you can do it quicker. And the second one is enable GPU, which allows you to switch between GPU and CPU implementation of the matching. So I'm gonna pass this enable GPU to my step 2 to emergency match, and that's how I use. So I can switch here between a CUDA function and a CPU function. Basically that's it. And then I'm going to go back here. I go through step 2 to the grouping step. Then I'm going to the step 4, the training, the model training step. Here, when I come here, I should have my merged and grouped the data already. And I'm gonna break this into train and test data sets, right? Also to validate my model. So I use the ratios of 80 and 20%. I'm gonna split this and gonna pass this to my deep learning model to train. Okay, if you wanna run this application here, it should end up with the following output. So a few hours ago I ran this application here, and this is the output for my model, which should be printed out after every execution. So basically I have the metrics for my regression for both the train dataset and the test. So it's quite a bit of information, but most importantly you can see that my R-square metric is 95 for both train and test. This is a really good sign. It means our model learned really well the frequency based on our set of features. Besides having a precise model, another important point is the time of execution. So Spark is really good because it allows us to see real easy the timeline and how long it took for each stage in your application. You can see that I started running this 3 o'clock and it took about more than 2 hours, and even I have 2 nodes, 2 executors, and most of the time it took this job 3, which is related to the distance computation, and it's related to the pre-processing stage, right? So the pre-processing actually takes longer than the training itself. That's why it's really unfeasible I found really unfeasible to run this using only one executor. You can do it though by using a subset of your data. However, keep in mind that your model will be useless if you use too little data, right? So just keep that in mind before running. I hope I was able to demonstrate a little bit about my application. If you have further questions, please go please check out the README in my GitHub project, which is quite simple and tells how to run this application. Also feel free to go through the source code for my application, which is really easy to understand and also pretty well documented. And I hope you enjoyed it. And that's how I end my talk today. So cheers.